Today we have the pleasure of having here Nick Cox. Nick Cox is an expert in interstellar medium, and in particular in molecules and organic material that is in there. He did his PhD in Amsterdam, and then he did several postdocs in Madrid, in Toulouse, in Leuven, Lovaina.
Yes, Louvain.
Louvain.
Well, Leuven if you want.
Okay. And right now he's working as a research engineer in Acri ST. And he's here because an activity that will take place tomorrow in the same room that I encourage all of you to come is going to be very interesting. It's about how we astronomers can use our abilities and to work in other fields, in industry and in other research areas, and he is one of the invited speakers. But today is time for astronomy, and it's time for interstellar medium, so I leave you here with his seminar about edibles and leaves.
Thank you very much, Anna, for your nice introduction. So yes, today I'm talking about science, because I still love science, even if I work in a company. That's possible. So tomorrow I will tell you more about how it is working in a company and how it relates to astrophysics, and how it does not relate to astrophysics, perhaps. But in any case, today I will tell you about the diffuse interstellar medium, and in particularly I want to talk about the diffuse interstellar bands and the interstellar dust grains. So this is work that I'm presenting on behalf of two groups, which are called Edibles and LIPS. These are all the people that are involved, and so let me point out, if I can, people that are doing the most of the work are Amin, Jonathan, and Miriam. Amin and Jonathan have doing a lot of the data reduction. Miriam has done a lot of analysis. Rosine, also Anna is on the list somewhere. I hope I did not forget her, yes. And then the LIPS group is a bit smaller. It's focusing on the dust part of the diffuse interstellar medium. So briefly, what I would like to show today in the next half hour or so is to briefly recap again what we mean by diffuse interstellar medium, what are the sort of the conditions and the stuff associated with this. Then I will tell you about the diffuse interstellar bands that Anna already discussed here 2 days ago. So what do we know and what don't we know about diffuse interstellar bands? It's really one of the biggest enigmas still in astrophysics, specifically spectroscopy. And then I tell you about the two surveys we have started, and we are now finally getting our first results of. So that's the ESO Diffuse Interstellar Bands Large Exploration Survey. You do everything to get a nice acronym, and the Large Interstellar Polarization Survey. So the diffuse interstellar medium. So basically what we consider the diffuse interstellar medium is all the gas and dust distributed between the stars. So that's the interstellar medium in general. You can see it because it's because it absorbs and polarizes starlight, which is coming from the further distances, and also in the longer wavelengths, this dust emits infrared emission. So it has a temperature. The gas itself absorbs starlight and emits photons at very specific transitions. So you have absorption features or emission features. This is a very general picture that I'm sure you all know. So for this talk, I'd like to focus a bit between at the very specific phase of the ISM. So you have a lot of different phases, from very hot ionized gas to very cold molecular cores or hot molecular cores, and everything in between. So here we discuss mostly the medium that's sort of cold and almost molecular, so between, let's say, 10 and 100 Kelvin, with number densities between 10 and 1,000 or so. Whereas usually there's still hydrogen and also molecular hydrogen with a certain fraction that shifts a bit. If you look at it more physically, here's a nice illustration by Snow and McCall in the survey. So here you can see how basically the different phases. You have diffuse atomic, diffuse molecular, translucent clouds, and dense molecular clouds. And the difference mainly you can see here is in the fraction of in the abundance of molecular hydrogen, which slowly increases when you get to the diffuse molecular part, and it rises when you get into the translucent clouds. On the other hand, you see here that the ionized carbon is more at the maximum here in diffuse clouds, and it slowly starts to decrease when you get into this translucent domain. And here you start to having CO. So basically what we're discussing here is this part, diffuse atomic molecular, and a little bit into the translucent part where you can still use stars as background sources to probe this medium. So you have extinctions up to 5 magnitudes or so. So what do we see? Generally, if you look at stars and the background stars, what we see is the extinction curve. So this is the interstellar extinction curve, which is mostly due to dust grains, this very large feature. So you have the far UV rise. So this is the UV part, and here it goes to the infrared. The most conspicuous feature is this UV bump. And then on top, which you cannot really see here, are lots of molecular transitions in the far UV, in the UV, in the optical, all kinds of atoms and molecules. So we already know quite a few of them. In the diffuse ISM, you have many atoms, molecules, and also in the molecular lines, which you can see in the submillimeter far infrared. So particularly Herschel has allowed us to probe absorption features in the diffuse ISM by looking at distant bright radio sources and far infrared sources. So another thing is here the infrared emission bands, which are thought to be due to pHs, polycyclic aromatic hydrocarbons, so large molecules constructed of different number of benzene rings. One interesting feature is that this extinction curve, there's a sort of mean in the galaxy, but there's a large variation. You can see here very large RV values, as we call total to selective extinction, up to very low values. So you have a large range in values. And even between different galaxies, you see here, this black one is the SMC extinction curve, which is very flat and has a very steep far UV rise. So also there's a lot of unidentified features, so we don't really know what this UV bump is. We believe it's some kind of carbonaceous material. Then you have here a few hundred diffuse interstellar bands in this region, so you can see here the spectrum, which also we don't really know what they are. We have extended red emission, blue luminescence, the 3.4 micron absorption band, and the aromatic infrared bands. And so it's quite a bit of uncertainty in what this really is. Only recently we have, the community has pinpointed a bit more accurately what this could be. So particularly the C60 molecule, the fullerene, Buckminster fullerene, has been detected in the mid-infrared in different environments. It has now also been detected in the diffuse ISM, where the signal is obviously much weaker. Here you can see the chameleon and scutum sidelines. So this is a chameleon dark cloud, molecular cloud, and here you have the more the translucent clouds. So you probe different clouds in each line of sight. But here you can see the two features that are attributed to C60 emission. And here's a reference spectrum of a PDR, where the signal has been detected much more clearly. So here we are really at the edge of the detection. With Spitzer, this was done. And with James Webb, we can, of course, go much deeper and more accurately probe the diffuse ISM. Of course, you also see the pH emission bands, but these are too generic to really pinpoint exactly what kind of molecule this belongs to. C60 is therefore one of the only ones, as well as C70, which has been seen in one planetary nebula. Then the other thing is that also C60, but the ion, the cation, so the ionized version, has been detected in already for 20 or so years. There were two absorption features detected in the near infrared around 1 micron. And finally, these have been identified with C60 plus through accurate lab measurements in the gas phase. I'll come back to this later because it's important in the whole story of the diffuse interstellar bands and what we can learn from them. So here's simply some numbers for C60. If you look at the emission, this is the fraction of C6 of interstellar gas phase carbon in C60. So it's 1 to 10 times 10 to the minus 5 in the emission. We get a similar number for the C60 plus in absorption, which you would expect sort of a balance. Because the ionization potential is about 7.6 eV, so you get, depending on how much extinction you have in your diffuse clouds, you get a decent ionization fraction. So just to say that in this graph, there's a lot of interconnections between, on the one hand, the gas phase, the molecular inventory, the dust grains, there's a lot of interaction between those different parts of the ISM, which are driven by very large, to a very large extent by the interstellar radiation field, so by the number of UV photons that these particles see, so a lot of photochemistry going on. And of course also the molecules and the dust are affected by the physical conditions, so you have densities and pressures that also affect the chemistry and also the physical conditions, so you can have grain destruction, you can have etc. So the relevance here for the diffuse interstellar bands, we're missing a large part of the interstellar astrochemistry, and so we lack really still a lot of detail about the cosmic carbon cycle and also the molecular complexity in space in general. I'll come back to this important point that I believe strongly that DIBS can be used as a very important diagnostic tool, even if you don't really accurately know each one what they are in terms of their carrier molecule or carrier something. We believe it's a molecule, but it's still open. So exploitation of diffuse bands does not require identification. And there's some advantages of using diffuse interstellar bands, which I will come to once I explain to you what are exactly diffuse interstellar bands. Maybe that's more logical to do. So diffuse interstellar bands are absorption features in the optical to near infrared, so between 4,000 angstrom up to 1.7 micron. They were discovered 100 years ago by this Marie-Elia Heger, who unfortunately did not continue in astrophysics after this discovery. So she did not, she created a problem but did nothing to really solve it. Today there's about 400 of these bands known. Here's a representation where the white line represents all the diffuse bands in the between 4,000 and 1 micron. You can see here there's a large concentration here at about 6,000. There's a few isolated bands here at the near infrared. And at the further infrared there's also about a dozen absorption features, but they get spread out to a much larger spectral range, so it's very sparse in the near infrared. So some are very strong, as you can see in this graph. There's about a dozen or so that are quite strong. Most are weak though, only in the order of a few milliangstroms, while the strong ones can be a few hundred milliangstroms. Some are broad, most are fairly narrow, so between half to 1 angstrom, and they can have, so in wave numbers, for the molecular spectroscopist, this is more important to know, between 80 and 280 wave numbers. So what you can see here is that there's a large range in widths, which also it has an impact on what kind of carriers it could be. So the different types of carriers give different types of absorption bands. Already, this width is too broad to consider it a molecule, a diatomic molecule, or a small atom, because they have much narrower line widths, less than 0.1 angstrom. So why do we think, why do I keep saying molecular carriers? Well, one of the features is that some of the diffuse bands, this is one of the strongest ones, they have this kind of signature substructure in them, which is not noise, it's really substructure, which is reminiscent of a molecular rotation profile of a large molecule. So from these peaks, from their separation, you can already guess with some assumptions on the temperature and the molecular constants that this could be a molecule between, let's say, 30 to 60 carbon atoms. But it depends a lot on your assumptions, so it could be a small linear molecule up to a large fluorine type of molecule. So we have not enough information to constrain what it is, but it suggests a rotational profile. Then also, interestingly, all these diffuse interstellar bands, they don't respond in a uniform way to changes in the environment. So different bands will respond differently to changing environments. So there's environments where you have a lot of strong UV radiation, effective UV photons, where one of these bands will grow very strong, while the other band almost remains the same in strength. So this is one reason why we believe that most of these, at least the strong ones, represent unique carriers. So there is one carrier for once, at least for the strong diffuse bands. Whether or not the very weak bands might be related to the strong ones, that's very difficult to say because of the difficulty to measure them very accurately in terms of uncertainties. So this also really you don't know. But the assumption is more or less one dip, one carrier for a large extent. In general, they relate when you have more dust in the line of sight, you have more dip absorption. If you have more gas in the line of sight, you have more dip absorption. So they seem to correlate with the rest of the diffuse interstellar medium, which does not tell you a whole lot, except that they are interstellar in nature and they really follow the in velocity, the profiles of the diffuse ISM, so the calcium 2 and the potassium and the CH molecules, CH plus molecules, they follow those radial velocities. So we know that they are really interstellar and associated to the cold or ionized ISM. They're also quite stable. We don't see changes in the bands over time, or very little, if any. They're widespread and abundant. So we see them, well, okay, let's fix this. So the total equivalent width is about 25 angstrom per unit reddening, which, again, taking some assumption about the strength of the feature, the oscillator strength of the molecule, the carrier, and the number of carbon atoms inside, and so on. This could be between, could be about 0.5% with an order of the factor of 10 uncertainty, of course with carbon, and quite a significant fraction of the par fractional abundance, so the pHs that are being studied through their infrared emission. Okay, so how do we know they are abundant? So we see them not only in the Milky Way, but in the Andromeda, in the LMC and the SMC. We see them in more distant supernova host galaxies, where the bright supernova can be used to probe the ISM of the host galaxy. And even here we see this difference between lines of sight which have a lot of UV and lines of sight which have little UV. So here you have a lot of UV, a little UV. So we can really, in these very distant galaxies already, use the diffuse bands to get some idea about the local conditions of the ISM in those galaxies. And this is, of course, something that Anna has been pioneering a little bit with MUSE, is to really do this in a sort of systematic mapping way. This is the early results, and this is the results she showed 2 days ago, which I find very impressive, where you can map these two bands, so the ones I showed here, basically. So these are these two, where we had some points in the local group and some points in towards supernova, but now really you can go to a distant galaxy, the antenna galaxy in this case, and you can really map these two diffuse bands. And if you know how these diffuse bands respond to an environment, you have a very accurate tracer of these environments, which you otherwise won't have. The advantage that Anna also showed is the diffuse bands are relatively broad, which means that if you want to detect them, it's sufficient to have a moderate resolution. So about a resolution of 5,000 is perfect. While if you would want to do the optical molecules or atoms, it's much more difficult to get a good handle on those. So that's a very nice direction, but we are taking another direction. But okay, carrier candidates, carbon change. So it could be something like this. It could be a very long one, short one. We don't know. The question is, of course, how did such a large linear molecule keep existing in interstellar space with a lot of UV photons? So something more stable are the pHs in all kinds of different configurations. These are usually quite stable against UV photons. So they reach a steady state with a hydrogenation level, and they can be quite stable. There have been studies in the ISS space station exposing them to the UV radiation, and they're quite stable. And also very stable are fullerenes, different configurations. So we have here the C60 fullerene, which has now been confirmedly identified in space. And of course, now people are looking for the other ones. But the first results indicate that all the other fullerenes have much weaker transitions in the optical, so they're not a direct solution for the diffuse interstellar bands. But if we can detect them, at least it will give us a handle on the kind of complexity we can expect in the interstellar medium. But of course, knowing C60 exists, and on the other hand, we have C2 and C3 molecules that exist, there's a large gap in between. And exactly to know and understand what these molecules are and if they are related to these diffuse interstellar bands is still a very big question. So people have, of course, so one way to do, to get the identification, the ultimate way to really know for sure, is to compare laboratory measurements that are done in the gas phase under similar conditions as the space conditions, so at low temperatures, low densities. You want to measure these spectra, so in this case pentacene, a neutral pentacene, and you want to compare it to the interstellar medium spectrum. Now there is a very almost a close match between these two features. Unfortunately, you see here also another strong feature for this molecule which is not there. And also if you look at the detailed profiles, they're not the same, so in this case we still reject this specific molecule as a carrier, but I think it's fair to say that this type of spectrum, which you can see here for pentacene, has some similarity to the interstellar spectrum you see with the different absorption features. So I think this is going the right way. One issue with this is that this is a neutral pH, and we expect most of the pHs to be ionized in the diffuse interstellar medium. But measuring ionized pHs in the lab is very difficult. So this is the first step, of course, and to get ionized species measured in the lab is a challenge. And indeed, this is one of the challenges for the C60 plus fullerene, which was first proposed in 1994 to correspond to 2 near-infrared dips, which you can see here. But unfortunately, the laboratory spectrum at the time were done not in the gas phase. So there was a shift between the laboratory spectra and the astronomical spectra. And without really knowing for sure what the shift is, you could not claim a detection. Because for detection, we have to have a few criteria, a bit similar to what's done in the millimeter domain. In this case, we want to have the stationary line, which is in a spectroscopic binary. It should be absent in unreddened lines. There should be 2+ transitions. It should match in wavelength and profile, so the profile and the wavelength should be very good match. Preferably, we like to have 2 independent measurements to identify a molecule in space, so not only a dip, but if it could be confirmed by millimeter observations or infrared observations, that would be a very big plus. Of course, you need to detect it in multiple objects and preferably in multiple instruments, just to rule out you have some instrumental bias. So what's the deal with C60 plus? It was a very nice experiment done only a few years ago by Ewan Campbell in John Mayer's group in Switzerland. They obtained this gas phase spectrum using helium droplets technique, and you can see here 4 bands, and these are the 2 strongest bands which correspond with these 2 bands. So the lines here are the positions of the interstellar spectrum, so we have 2 satellites band. So this was a very nice experiment. A lot of follow-up experiments have been done in the last few years, people to define exactly the profile of these bands, the weak structure, the ratio between the different bands, etc. Now the problem with these 2 bands is that they fall in the near-infrared region, where there's a lot of telluric absorption lines. So even on using spectrograph Espadon on Hawaii, which was a very dry situation, it's very difficult to remove these strong telluric lines, which are in many cases saturated, and retrieve the underlying true continuum and features. So here you can see the strongest bands, which is clearly detected, but here trying to see the weaker bands is fairly impossible. So one solution we thought of was to go to space and use the Hubble Space Telescope STIS instrument to take a near-infrared spectrum. So for the first time we were able to demonstrate it possible to take a very high signal-to-noise spectrum with STIS using a scanning technique. So you scan the star along the slit, and then you remove all the strong fringing that's in the CCD. And you get this very nice, very flat spectrum with a lot of stellar features, of course, and here you have a few interstellar features, a few new diffuse interstellar bands. And the C60 plus bands are here, so this is very convincing. And then here it should be very weak, and here very weak. So if you look a bit more detailed, you can see here this is the reference, this is the strong band, what we expect. So unfortunately this does not cover this band in this setting, so we lose this. But we were looking for these 2 smaller bands to really confirm that C60 plus is the carrier of this strong band. So here you can see the 9428 band. It's sort of there for this band. I won't say too much. And this one is also very difficult to see. So we're trying to follow up with this to get spectra for multiple targets to really try to confirm whether or not these bands are there, and I think that will be really the nail in the coffin, so to say, of the C60 plus identification. So the issue at this point is the relative strength of the two weaker satellite bands. Also, the new measurements in the lab have changed those ratios a bit. So it seems now that this band is actually a bit weaker than that band. So maybe that could help us to explain what we saw in this spectra. The other issue is that in the astronomical observations, the ratio between these two strong bands, these two, varies quite a bit. So there's not a very good correlation. I mean, there's a correlation with a Pearson correlation of 0.8 or so, but there's quite some significant variation between the two. Now, this one suffers a bit from stellar contamination, but even trying to correct for that, you get quite a large, you'll get some change in the ratios. So whether this is something observationally or maybe we are looking at an effect of the molecule itself. So could be reasons, molecular physics reasons, why these two bands would have slightly different populations for different temperatures of the ISM. So the next step will be to relate those ratio variations to the conditions of the ISM, so to the temperature of the other molecules, to the mostly the temperature will probably be a larger effect, but also radiation field could play a role. So that's something in progress. Okay, so we have a bit of time left. So actually the part I wanted to talk about is the edible survey and the LIP survey, which are a new effort really to make a sort of consolidated and uniform analysis and survey of the diffuse interstellar bands as in relation to the other to the molecules and the atoms we see also in this medium. And relate that in addition to the dust grains, because we know the dust is also important for the diffuse interstellar band carriers. In some way it could be a way to form molecules, so it could be a formation site, it could be where molecules get depleted onto grains when you go into denser environments. So clearly there is a relation with dust. So in general, what I try to convince you of is that DIPS point to a very important chapter in interstellar physics and chemistry that we really are only at the tip of knowing the details about. So of course one of the key questions is what is the DIP carrier exactly, but there's more than that. There's other questions like how are they and how are these species formed, excited, destroyed, what's the life cycle, how can we get more detail on this in different environments. And then what can these features tell us about the physical conditions of the environments? Of course, if you know the carrier, it's much more easier to use them and know a bit about the physical conditions and the chemical evolution. But I think the trick is to find out ways to use these diffuse interstellar bands as diagnostic tools to learn about formation, excitation, destruction of molecules, physical conditions, and chemical evolution, even when you don't know exactly for each band what their carrier is. And with C60 plus, I think we have a great starting point, and we can also relate the other diffuse bands to the C60 plus diffuse bands and see how they vary and what their relative behavior is in relation to a C60 plus behavior. Because they tell you a lot about the size and the excitation, ionization conditions, etc. So I wanted to show this plot because I think it's a very nice first approach of looking at a small sample of single cloud lines of sight. So lines of sight where you know you only have one single interstellar cloud between you and the star. And you look at a large number of diffuse interstellar bands and apply a principal component analysis where you also include extinction, you include hydrogen column density, H2 column density, you include the ratio between different diffuse bands. And you can see here that there's a result. So the principal component 1 is thought to primarily link with the total amount of gas in the line of sight. So the total amount of interstellar gas. and you can see here specifically this dip is a very good tracer, the best tracer of this amount of interstellar gas, the 5797, so the one we saw in Anna's map, and one of the two stronger ones, which is next to the 5780, which is more up here. What we also see is here we have the molecular hydrogen fraction and this ratio have a similar kind of correlation. So in the PC2, what we believe it's related primarily to the, it's not exactly the strength of the interstellar radiation field, but we believe that if you look at the analysis that it's sort of correlated with the, it's sort of related to the interstellar radiation field strength. So we see here really this differentiation between species that respond positively, so these 5780, these are a bit broader diffuse bands in fact. And here you have the ones that respond a bit more negatively, which are typically more narrow features. And this already tells you maybe a bit about the kind of carrier you could possibly have. So for example, ionized pHs, they tend to have broader absorption features than neutral pHs. So you could have ionized carriers versus more neutral carriers, for example. And it's also nice to see that this ratio was known already to relate very well to the local interstellar radiation field from studies of different star-forming regions, OBE associations. And you can see this again in this principal component analysis, that there's quite a strong correlation with the radiation field. And also H2 is strongly correlated with the radiation field as expected from simple models. Because you get H2 when enough of the UV photons are being attenuated in your cloud and you start forming H2. That's an important point. So the purpose was to carry out a systematic and sensitive survey to establish quantitative relations. So for that we started a large program on the VLT UVIS, which is running for about 300 hours, so about 30 nights. We're very close to completion. It's been taking a bit longer than expected because we are relying on bad seeing conditions at the VLT, so we take advantage of where there's lots of high seeing, or thick cloud layers, because the stars we're looking at are quite bright, so they're 5, 6, 7 magnitudes. So we can look at them in twilight even and get a very good spectra. We're just taking many spectra, so it takes a bit longer, but at least we get a lot of nice spectrum by using these bad weather conditions. So in some sense we always hope for bad weather on the VLT to get our things done. But so it's been running for 8 periods now, so that's a bit longer than the 4 periods anticipated, but we're very near to completion today. So we have about 120 targets, mostly OMB stars. So the special thing here is that we go really from the near UV 300 nanometers to 1 micron and everything in between using the different settings of the instrument. So we get a lot of information on atomic and molecular lines. We reach this signal to noise of 1000 in the red, so around 6000 angstroms. And in the blue, the UV, we get about 300-400 signal to noise, which is very good, especially considering also that we have a quite high spectral resolution, 80,000 in the blue, up to 100,000 in the red part. So these are our targets. Just to show, they're mostly low galactic latitudes and obviously oriented to the southern sky. We try to have a sample which is a representation of different conditions in terms of the dust, in terms of the type of dust. So the RV indicates the grain size, the hydrogen density, the fractional H2 fraction, and different element depletion patterns. So, time to show you a few of our first results. It's been quite an effort to get all these spectra in line and reach this high signal to noise. Because if you, one of the issues was in fact that in the standard procedures, the number of flat fields that you take is not high enough. So we had to demand to have extra flat fields taken during the day so that we can take hundreds of flat fields. They could even be taken over several weeks. We can combine them and then use them to do the reduction, because it removes a lot of our extra features that you get when you try to go to a signal to noise of 1,000, because you're at the signal to noise of 200 for individual spectra, you're already hitting this limit of the standard number of flat fields that are usually obtained. So that was one of the issues that we had to solve, and there were other issues with as well with calibration, etc. But anyway, we succeeded, and I hope you can see it here. It's a bit, maybe not very high contrast, but what I show here are mostly atomic and molecular features in the UV part. So really at 3,000, 310, 330 nanometers, very far in the UV. We have here at the top OH+, CH+, CH, all very weak features. So we can see here that the spectra look very nice, considering that these are only like 1% of depth. So this was a very nice. Well, we were very happy with this result, and this allowed us to do an interesting study which concerns the cosmic ionization rate, because you can try to estimate the cosmic ray ionization rate from the OH+ abundance, because OH+ is a key molecule in the whole scenario of H2 formation to H2O+, etc. And here there's an important contribution by the cosmic ionization rate, which drives this balance. So what we did is, so the key thing here is that we now could, for the first time, not only have one OH+ line, but really have a whole set of OH+ lines in the UV. So up to 10 different OH+ lines could be detected in the small UV range, which was very well. Before it was much more difficult, and there were usually only 1 or 2 or 3 lines detected. But now you can see here these are the equivalent width versus the basically the column density. Well, not the column density, because the fit gives you the column density. So you can sort of get a more accurate kind of estimate of the OH+ abundance. And with this formula, which is here the cosmic ionization rate, you can relate the abundance of OH+, the column density, I should say, and the column density of the H, the total hydrogen, so atomic and molecular, and you get the cosmic ray ionization rate. So we did that, and in fact we had to revise this ionization rate because there were some factors not included before. That said, it's still a sort of rough estimate, because there's still assumptions about the temperature inside, and assumptions on the fraction of molecular hydrogen inside. But this is a reasonable estimate, I think, and these are our results. So in this work we had 10 targets where we could have 3 or more transitions, and then we had also 28 targets where we found only the strongest bands, either because the strongest band was very weak or the signal to noise was not as great as the other spectra. So these are our results, and then we compare them with results from the literature. Rescaling, of course, their results to our new cosmic ray ionization rate equation that I showed before. So these are the previous results, and then you can compare here with infrared. This is based on H3+, near infrared, and also submillimeter with Herschel OH+ based cosmic ray ionization rate. You can see here our sort of range. So there's quite a big range. In fact, how this relates to other. So now the next step would be to also see if there's any effect with diffuse interstellar bands, with some of the diffuse interstellar bands, to see what the cosmic ray ionization rate could do. Also to say that the survey also yields a lot of interesting stuff, but it's not necessarily directly diffuse interstellar band related, but in general ISM physics, and as I will show also stellar astrophysics can benefit from our survey. So another results, which also we are very excited about, is that we can now have these profiles of quite weak diffuse bands, and you can see here these show again the substructure that I talked before. So here you have 2 peaks, and here you have possibly 3 peaks in these weak bands. And particularly what's interesting, that these 3 bands are very strongly correlated with C2 molecule. So where you have a lot of C2 molecules, you also see strong bands, which from their profile, from the substructure, which we really see for the first time, in all these C2, so all the 10 C2 dips, we can see this kind of substructure. So we see now a very strong link between a small molecule C2 and potentially a somewhat larger molecule, and that they are existing in the same environment. So the top one is a stacked spectrum of the bottom individual spectra. And now, of course, we need to try to see if we can do some modeling or reproduce these profiles, because they give you insight on the temperature and rotational constants, as well as to see if here we have profile variations between individual different sidelines to probe temperature effects, for example. Another issue is that we tried also to contribute to the whole debate that was going on for C60+, because people were saying, okay, we see those two weaker bands. No, we don't see those two weaker bands. People using the same data and coming to two different conclusions. That also, I guess, shows you how interpretation analysis of spectra can have a human side to it, because if one person sees features and the other person doesn't see features, I guess there's some kind of bias also in what you want to see sometimes. In any case, we try to confirm this 9428 band here, but as you can see, the telluric absorption is huge, it's very strong, so it's very difficult to really confirm this, but we thought this was in line with the laboratory expectation, a bit weaker, but as I said, the lab has changed, so now it should be a bit weaker. And we found here possibly, there's another dip here, which was in the okay, so another thing which you can do, if you see here all these telluric lines, they are in the telluric rest frame, but the interstellar absorption is in a different rest frame, right? So depending also on the observing date, you get shifts between the telluric lines and the interstellar feature. So if you have lots of spectra with of this band, which is at different velocities and different radial velocities for different lines of sight, and your telluric lines also shift with respect to that, you can reconstruct the telluric free profile, in this case of the strongest 9577 band, where here you can see in color the number of individual spectrum that were used to construct this particular data point. So you can see here that at the regions where there's a lot of telluric lines, you have only few spectra, or you have few spectra here, you have very few here, so none, very strong telluric. But in this way you can reconstruct this profile, and what you see here, what's very interesting, and what we're working on to understand right now is two things. You see here this substructure again. So again, this is well, we know it's a molecule, right, C60. But the laboratory data are not good enough to show this kind of substructure. So this is, of course, very neat that in astrophysics we can now give something back to the laboratory astrophysics in terms of, okay, we see this substructure, can you also find that? And then also the profile in the band, these large wings, are also very interesting because they give you also information on the lifetime of the molecule. So you have lifetime broadening, which broadens your profile. So this is a very interesting result, I believe, and now it's up to also the molecular physicists to understand exactly why you get this substructure in this way and what these wings are, etc. And try to see if we can go back to the laboratory to uncover this as well. Okay. Edibles is also good for stellar astrophysics. So here I show an example where by serendipity we picked up this changing spectrum in this star 148927, central star of this nice nebula. This instigated a reanalysis of the previous spectrum, follow-up spectra, etc. And it turned out that, in fact, what we have here in the center is an eccentric high-mass binary containing a magnetic O star. So this was already, the star was already well studied by people in polarimetry, so the magnetic atmosphere. Now we discovered as, in fact, it's a long-term binary. It has a period of almost 9,000 days. So it's, it takes some time to do the orbital coverage. So I think that was a nice example because that's what we wrote in our proposal, that it could also be useful possibly for stellar astrophysics. I guess that's what you write in a proposal, but if it actually comes through, I think it's also very, very neat. So there's lots of things to do in terms of analyzing the profiles, analyzing the other atoms like C2, C3. You can get a lot of information from those. It's really, it's almost too much information you can get from the spectra, so we have to sort of focus on small bits and pieces, because if you want to do everything at once, you start losing the oversight and you get lost too easily. So quickly, if I have time, I want to relate this as well to the LIPS survey, which is a large interstellar polarization survey. This was a short survey on the VLT. It took 2 semesters. It was also filler type. And we observed 140 stars with a large overlap with edibles to make sure we get the same kind of, we could use the information for both surveys. But we included also some other interesting targets which had high extinction. It's optical, force 2, has a moderate resolution of 900, and we get the limitation of 0.1% in the linear polarization. As a reminder, this is the polarization per extinction curve. So here you have the optical, which is represented very often by the Sierkowski parameterization, which has a maximum polarization. It has a decay parameter, which indicates the width of this curve, and it has the lambda max, which basically says where your maximum is. So that's the 3 kind of parameters. So lambda max and k have been measured for other targets before, and there's a large spread, and probably this is related to dust evolution. So in dust grains change in size and composition, you get a different kind of polarization. And indeed, so briefly the survey, you see here the targets, similar kind of distribution as edibles. Here's a nice example. So in purple is the intensity spectrum, and cyan yellow gives you the polarization curve here, and here the position angle curve, function of wavelength. Very nice data. We could derive Sierkowski parameters for about 70 sightlines. The others were either too irregular or too low signal-to-noise to derive parameters. Everything is on Vizier. You can download the spectra at different rebinning factors and look at that to get your favorite targets. So here, so the first thing, one of the things we decided to do was to look at try to reproduce the polarization by modeling. So this was led by Ralf Siebenmorgen at ESO, who had some very good models for the UV extinction, and he included some polarization part of the modeling. So what was the benefit of including polarization? So 2 things changed when including or not including the polarization information. Is first that with polarization you get a steeper curve, a steeper slope of the particle distribution, so which means you have relatively more smaller grains, and yes, and the larger average radius of the amorphous carbon grains. So your average size also went up. Steeper slope, no, I should say it's more larger, relatively more larger species. So this is the whole plot, similar lambda max k that we have in cyan is our colors, and you have previous surveys which were not spectropolarimetry surveys, but they were broadband polarization surveys, so they were like BV, I, J kind of polarimetry, whereas we are now doing the curve fitting on spectra which have a moderate resolution, and you can get quite accurate results. I believe they're more accurate than before. So when we started, Ralf was interested, we were all interested to look at, we started looking at all the data points, but then we realized that maybe it's better to look also at data points which we know from optical spectra are only probing a single cloud line of sight. So we try to isolate those and look at their behavior with respect to the entire sample. So what we find is that in fact there are some strong correlations that we only discover when we look at single clouds. This is a bit the same like what I showed before with the edibles, with the principal component analysis. This was also for single clouds, and this kind of strong correlations, they tend to get smeared out when you have too many clouds in your line of sight. You don't really know which cloud is doing what. So here we see that with including this or only looking at the single clouds, you now suddenly get a much stronger correlation between the extinction bump, so the UV bump, and the mass ratio of total silicon to carbon. And we did some tests on Monte Carlo and some significance tests to see that really this is a significant result. It's not just because you have fewer points that you get a better correlation. It's really significant. And the same way we see here, total to selective extinction RV, which has been always considered as a tracer of the size of dust grains. So indeed, it correlates with Q, which is the exponent of the size distribution. So you see here that you have a flatter distribution where you have higher RV, so you have more large grains. So very nice to, so this is confirming basically what we already sort of knew, but it shows a very nice correlation now, and it's quite strong evidence. The second point is that also we looked at this in terms of comparing with this Yarkovsky parameterization, which is just a parameterization. It doesn't necessarily tell you anything physical. But if you now look at our fitting of the models, you can see here that lambda max is in fact quite well related to the mean radius of the aligned silicates. This is also what you expect from the model, but it's good to see this confirmed by observations, because in the model you can also see that the lambda max changes with this value. And then you have the width of the curve relates to the minimum radius of the aligned silicates. So you see here that again you uncover this nice correlation only when you're looking at single cloud lines of sight. So that's also something to consider in this kind of dip studies and dust studies, that if you have too many different clouds in your line of sight, you start to confuse things, which might not always help in understanding. And this is still also maybe one of the issues that Anna sees when looking at the entire galaxy, that, you know, what are you comparing things that are like or not, especially. But okay, you have to do what you can with what you have, but okay, so this we could do. So now we're trying to extend our sample with single cloud lines of sight. We still have 50 targets that were observed with ISIS on the William Herschel, but reduction has taken a bit longer than for FORST-2. Apparently it's a bit more complicated to get rid of all the systematics and the polarization, but hopefully that's coming soon, and then we can add another 50 targets and hopefully quite a few more single cloud targets in this plot to really confirm these kind of findings. And so that's my last slide. Finally, so I just want to reiterate briefly that edibles will hopefully turn dips into very powerful diagnostics, which everyone can use for their own benefit, to study interstellar physics, to study galaxies, also for stellar studies. It's often very important to know what's in front of you and the star that you're interested in. To know, hopefully it will also help us to more narrow down the identity of the carriers of the diffuse interstellar bands, and guide laboratory measurements in this area, and even open a new chapter in interstellar physics and chemistry in that sense. And then finally, LIPS will support edibles in terms of understanding the dust grains in each environment, but in itself it's also a very powerful probe to study dust evolution in our galaxy, and trying to link the different variations in the polarization to the different regions in the galaxies, and to dust evolution models. So there's many dust evolution models that predict how dust grains grow and get destroyed during the lifetime of the galaxies, and with this we can also contribute to that. And I thank you very much for your attention all this time. Thank you.
Thanks to Nick for this talk. There is some time for questions. Is there one question?
Yeah.
Question, comments?
Thanks for the very nice talk. From the identified dips, do you have any idea of their properties if they emit in the radio domain?
So there have been some claims that there were optical dips that were due to C2H2, something like this. And they have searched in the infrared and they couldn't find anything. or in the millimeter, they could not find anything. And for the C60, I think they only have infrared emission, mid-infrared, and they might have a millimeter signature, but they have many, many rotational lines, so they will be very weak, and it will be like a forest of very weak feature.
And even at lower frequencies, between 10 and 60 gigahertz, do you have any idea?
I don't know if there should be any, maybe someone can calculate that.
Thank you.
But C60 is a very weird, interesting molecule. It's very difficult to calculate. Even these electronic bands, you cannot really get a strong handle. If you try to do quantum calculations, TD-TFT, you get degenerate because of high symmetry, and if you ask those people, it gets a mess. Sorry.
So yeah, I was wondering, did you find any correlation between the C60 plus divs and the strength of the NUV bump? Or would you expect any?
Between the UV bump?
The NUV, the 2175, yeah.
Well, it's not been done yet, as far as I know.
Would you expect it?
Well, no, yes and no. Roughly in the sense that more C60 should also give more carbon, but since the UV bump is probably a agglomeration of all kinds of different carbon, you lose a lot of the one-to-one correlation. And also C60. So one thing we're looking for is C60 neutral, but the transitions are weaker. And okay, difficult to find even when we look at our high signal-to-noise data. It's not obvious that there's any C60 neutral yet. I would expect the C60 neutral to be more with the UV bump.
Just one quick question as well. You were mentioning the measurements through single cloud, and then when you have several clouds and it gets more complicated. I imagine this is along the same lines as you go from an extinction towards an attenuation when you're observing through galaxies. So basically you get scattered light coming into your line of sight. Is that the reason why single versus multiple cloud is more complex?
It could be a reason, but what we see for the polarization is indeed that you have multiple clouds, it tends to depolarize. So they tend to have a lower polarization when you look at multiple clouds. If scattering into the beam is an issue, I'm not sure.
Yeah, because the thing is, for instance, when you're doing the attenuation loss in galaxies, the problem is you have not only the properties of the dust, but then you also have the distribution, the geometry of the dust within the star, so that will cause an effective attenuation that can be very different from the intrinsic extinction. So I'm wondering, if you even have single measurements and you have several clouds, would you have a problem, in a way, lower order, but a similar problem to this one?
It would be there, yes, but I think indeed it would be much smaller because you're looking at much more pinpoint kind of observations. Because I guess in galaxies where you have in your beam lots of stuff, a lot more than you would have when you're looking at nearby OB star.
I see that you regarding these diffuse interstellar features, you are tracing many positions in the Milky Way. Are they related to regions of star formation specifically? Could you pinpoint the star forming regions and these features becoming stronger?
So one thing that's been coming out recently is when people try to map, for example, near-infrared dips, which can probe a much larger extinction, that we see that if you look at star-forming regions, there are diffuse bands like Taurus, Orion, all these, but the dips, they tend to get depleted per unit extinction when you go deeper into the clouds. So there's a weakening, there's a decrease of diffuse band barriers when you go inside the clouds. So you see stronger at the edges, I guess, when you have the very dense regions. The dips are stronger per unit reddening at the edges than inside.
Because I think if I understood correctly, you tried originally to see whether there could be a relation with the pH features.
It would be nice to find a relation, but it's difficult again because we are looking at an distinction towards the background star, and infrared emission is probing the whole line of sight. So we still, to this date, we have not found a really good object target where we can study both at the same time and know that we're probing the same column of material.
So, as you say, you get your information from absorption, looking at the stars. Have you tried going to very bright emission nebulae, like for example, I'm thinking on Pleiades, where you can clearly see that in between a star you have light that is likely associated to gas or dust. So in principle, the super brightness is feasible for the largest telescopes. So why don't you get the spectra directly from there?
A spectrum from the diffuse optical emission between the stars.
For example? So, for example, in the Pleiades, why don't you, I mean, you can put Muse or whatever. I mean, I don't know whether Pleiades is visible from the south, but I'm just thinking on something that anyone can imagine that it has emission in between stars that you can see clearly by the eye. It could be reflection, I don't know what is that. But
we do see the extended red emission in this kind of environments, and blue luminescence, for example, reflection nebula. But this is more, these are much broader, larger features, right? I don't think at this point we've been able to measure narrow features in that kind of spectrum. I'm not sure anyone tried. I did not.
I'm aware, for example, of spectra using Sloan of all the fibers that were not pointing to any particular place, but for the sky. So someone stuck all that spectrum, spectra,
but
and
you
got
would look at absorption feature, or you would look at the corresponding emission feature. That's okay.
I mean, they have found diffuse interstellar bands just pointing random. So, I mean, I can imagine that what they have been measuring is the galactic cirrus, or so there should be information there as well, no?
Yeah, that sounds quite interesting. Yes, I am not aware of this particular observation.
So let's talk later.
Yeah, thanks.
There is no one.
Yeah, Anna was showing a plot talking about the interstellar radiation field versus the dips. So, is it a well-known correlation between both over the galaxy, or is it in the effect of the interstellar radiation fields of the strains of the dips?
So we have found that for two specific dips, their ratio seems to more or less correlate with the interstellar radiation field, but it's called the sigma zeta effect. It's been known for some time to exist. That some lines of sight which have a small ratio, they have also more molecules, and with a large ratio they have fewer molecules. And it seems to be that environments with more UV radiation have one ratio, or higher ratio compared to the other. So this is a sort of a general trend. There are a few regions where we were able to study it in a bit more detail, like the plot that Anna showed was from the Scorpius region, where we could study it in a small OB association. So we believe this is a general effect.
Okay.
Could be this, you see it in the supernova galaxies, you see differences.
Okay, thank
Of
you.
course, you can imagine that with 400 dip band, you will be able to have many more of these kind of diagnostics. So we try to look for those.
Thank you again, Nick, and we can still talking at the cafeteria. There is a table with snack and coffee. So, thank you.
Thank you.